So now we're going to talk about the last distribution in discrete probability distribution, that is geometric distribution. So far, you know the difference between Bernoulli, binomial, and Poisson distribution. In Bernoulli distribution, we divide into intervals of a one time. And if we set that interval into n times, then it becomes binomial. And if when we have a parameter lambda, then it becomes Poisson distribution. Now, what's the difference between hypergeometric distribution? So far, Bernoulli, we have only two possible outcomes. So the important properties are, you can see the important things we need to assume. Property to assume. If you can't see, just let me know instantly, right? So property to assume, first one is that we have two possible outcomes. Right? That is success or failure, head or tail, true or false, right? So that's the first thing we cover. Second thing we cover that we know. Yeah, so first thing is that there are two possibilities. Second thing is the possibility that every successive trial or experiment is independent. Right? What does this mean? So that is independent. What does that mean? For example, let's say we have a bag, right? That's a bag, and in the bag there are 4 balls, 2 black balls and 2 blue balls. So what is the probability that if I pick the ball and that ball is a blue one? So what is the probability of a blue ball? Of course, 2 by 4, right? Now I have to do a successive trial, another experiment which is next to the first interval and experiment, and I put this ball again back into the bag, and then I get like another ball, and that ball is a black ball. So what is the possibility of that black ball is 2 by 4 again, or again even if it's blue ball, so what's the possibility of blue ball is 2 by 4. So it means I replace, so if I replace the ball back in the bag, so this trial is independent. All right. Next time means every trial is independent of the previous trial. That's about the independence. So far we have talked about this, right? That successive trials are independent. Now, if we say that the possibility that every successive trial is dependent, that means when I pick the first ball, I don't replace it. If I don't replace the ball back in the bag, then first time the probability of a blue ball is 2 by 4. Next time the probability I pick and it was a blue ball. So what's the probability of a blue ball? Is 1 by 3. And if the ball is black, then its probability will be 2 by 3. So this is the successive chances of two outcomes, right? 1 by 3 and 2 by 3. Similarly, if I don't put this one and next time, the third trial, what is the possibility of a, because blue ball, if the second probability is, second time is also blue balls, and it means there are only 2 black left, so the probability of a black will be 1 by 2. And if there is black ball in the second time, then the probability of a blue is also 1 by 2. So in this case, I'm not replacing the ball, and that means that our second experiment is depending on the outcome of the first experiment. Do you understand this? Right? And the third experiment depends on the outcome of the second experiment. So then it's known as a hypergeometric distribution. If this is the case, then it's known as hypergeometric distribution. Right? That is, we don't replace the blue ball. So in successive trial, the probability is 1 by 3. So that's how the probability is because of the previous trial. Now you understood the hypergeometric distribution. Let's talk more on Alright, so I don't know, it's not working. Can you hear me? So if you can hear me clearly, I move forward. So now you understood the hypergeometric distribution. Now let's take an example. So remember, in hypergeometric, we don't replace the event. Let's see that I have to select 12-person jury. What is jury? Jury is a team of people which can decide for anyone who is guilty or not in a courtyard. The person to be selected for the trial from a pool of total 24 people. Sorry, there was some issues with the mic. So a 12-person jury have to select to be selected from a trial from a pool of 10 men and 14 women. So I have to select 12 people from 10 men and 14 women. What is the probability that this jury contains exactly 4 men? So you see, how, first I have to consider, means we have to know that is it a binomial distribution or is it a hypergeometric distribution. Either you can select someone or you don't select someone. So there are two outcomes for sure, right? So if it's a binomial, if it's a binomial distribution, then the successive trial should be independent. If it's a hypergeometric distribution, then the successive trial should be dependent. So as we see that from total 24 people, if I select you as one, and I say, okay, you step aside because you are being selected for in 12-member team. So I won't, next time when I'm gonna pick from 23. I'm not gonna pick from 24 students or 24 people, right? So I will not ask you that, okay, I have selected you, now you sit again, and then I'm gonna select you again. No, 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 no. Then you are not going to be replaced in the team, in the pool, right? So you will be selected. So next time I have to select one from the 23. So here, what are the chances? Let's see. So n is total number. That is 24. K, let's say, is a number of men, because that's exactly what we need to know. Number of men in the pool, right, which is 10. X is number of men chosen, which is 4, and small n, total number of people chosen, including men and women. That's 12. So these 4 parameters are given, right? Based on this, we have to calculate the probability of x equal to 4, right? Remember this. Let me tell you the probability function in a hypergeometric, and then we will see that how we calculated that. So probability of x equal to x, small x, is k combination of x, n minus k and n minus x divided by n power n combination of n. So this means that these 4 men, how many different ways we can choose 4 men out of total number of men, 10. Right? So what are the different ways? How many different ways? For example, if you have like 1, 2, 3, 4, and I ask you to select 2 numbers from these 4 numbers, so there can be different possible ways. Or 1, 2 is one possibility, 2, 3 is another possibility, 2, 4 is another possibility, 3, 4 is another possibility, and 4, 1 is another possibility, 3, 1 is another possibility. So these are different possibilities. So these combinations tells us how to calculate that, right? So if probability of x equal to 4, so in our equation, in our example, we just put the values. K is 10, so Cx is 4, n minus k is 24 minus 10, and n minus x is 24 minus 12 upon n 24 C12. So that's how we can calculate the probability function of x equal to 4, which can be, you can say 10 factorial upon 4 factorial into 6 factorial, right? 10 minus 4 is 6 times 14 factorial upon 8 factorial, and 14 minus 8 again 6 factorial, right? Divided by 24 factorial upon 12 factorial. We have learned this, and there's the formula, right? 24 minus 4, 12 factorial. So after solving that, let's say you get some value, which is 19.43 example, right? I'm not sure if it's exactly the same or not, but let's say if it's 19.43 or 0.1943. So 19.43%. So we can say that there is a possibility that 19.43% are the chances that exactly 4 men are included in this 12-person jury, right? And of course, you can also get the Q for x equal to 4. So that's how we get the hypergeometric probability distribution. Now let's talk about the parameters. So let's see the function. We know the probability function of this. Now, is it clear? If it's clear, then we move ahead. I'm doing the calculation slowly so that you can follow me correctly. So let's say x variable, I have to select small x from a probability function, from a function of x which is given as k x n minus k n minus x by n factor combination of n. So these are the combinations. We already know this equation. We know what is the probability of mean. We know how to calculate mean, which is expected value of x, which means sum of x into f of x in general, right? Where x equal to 0 and to n. So if this is the case, we can easily calculate it. So just put the values here. So we're gonna replace this value of f of x here, and we get what? We get sum of x equal to 0 to n and x as it is, and then put this value here. K x n minus k n minus x upon n cn. Right? That's what we get. Now we can simplify this one. So take this out and just try to simplify it. So we can say x k x can be written as x k factorial upon x factorial and k minus x factorial, right? And this can be further can be written as x k factorial upon x into x minus 1 factorial k minus x factorial. So you can divide this, it's gone. So now you are remained with k factorial. So I'm just gonna write here. So you're remaining with k factorial upon x minus 1 factorial and k minus x factorial. I didn't open it yet, remaining. So I just open x factorial to x so that I can cancel out this x. Now, we know that if k minus 1 and we subtract minus x minus 1, what will we get? So we get, this will be plus and there will be no bracket here. So minus 1 will be cancelled out. It can give us k minus x. So based on this, we can play with this. How we can do? We can rewrite this as k times k minus 1 factorial upon x minus 1 and k minus x. So see, this can give us the combination. This can give us the combination of k times k minus 1 combination with x minus 1 combination, right? So now substitute this value back instead of this. So what will we get? Because this is equal, right? Do you understand? This is equal. So when we substitute this value in here, what will we get? So I'm gonna erase this, okay? So if I substitute that value, this right here, it will give me what? It will give me summation x tends to 1, because this will be changed, because now we don't have that, and it will be k minus 1 x minus 1. That's what we have changed with, n minus k, and remaining n minus x is as it is, combination of this upon n the n. Now usually we can add up this combination, but because it's not 0, so we can't add these combinations. So to make this into a 0 form, what we do, we can simply solve it by letting that y equal to x minus 1, so that sorry, if x equal to 1, y will be 0, right? And x will be y plus 1. So y will be n minus 1. Right? Do you understand? X minus 1, sorry. So that's we know. Just simply put the same thing here so that I can get x. If x equal to 1, it means y equal to 0, right? So can I rewrite this equation as sum of y equal to 0 and x is n, so y will be n minus 1. Yeah, that was n minus 1, right? So it will be up to n minus 1 and times k times, here it will be k minus 1 and x minus 1. What is x minus 1? Sorry, x minus 1. X minus 1 is y. So I will take it as y. And n minus k, n minus y plus 1, because x is y plus 1. So I'm just putting the values, and by n cn. That's I can get, right? By assuming this one. So I'm erasing this right now. So this one and this one are constant, so I take it outside. So it will give me k n, right? K by nn summation. Now because I can add up, because now this is 0, so I can add these two, so it will give me times k minus 1 plus n minus k y plus n minus y minus 1. So this will cancel out, this will cancel out, so this can give me k upon n combination of n times n minus 1 upon n minus 1. Oops, it's a combination. This one, right? So that's our mu. So I'm erasing it directly to this step. I'm sure you're not getting bored, right? So k upon n, ncn, I open it, n factorial upon n factorial n minus n factorial. I just open this one times, so this can go up, n factorial n minus n factorial. I just solve this, open it and solve this, because this is in denominator, times n minus 1 factorial upon n small n minus 1 factorial into n minus n factorial. Right? So this n minus n factorial and this one will cancel out. And if I open this n factorial, this is n factorial, it can give me kn times n minus 1 factorial upon n factorial, n into n minus 1 factorial times n minus 1 factorial upon n minus 1 factorial. So this will cancel out. So it remain give me kn upon n. So that's our parameter mu. So that's how we get here k upon n. Right? So we can say that our mu is k n upon n, or n times k upon n. So what does that mean? In binomial, we have already learned that, let's talk later, but so variance in this, I'm not going to prove the variance. So variance can be denoted in hypergeometric as nk times n minus k upon n square, n minus n upon n minus 1. So remember this. Let me write it in a different way. So variance of x will be, variance of x will be n k upon n n minus k upon n times n minus n upon n minus 1. Right? Remember, this is divided, this is not a combination, okay? So that's our variance, that's our mu. Now see the property. We know, let's say proportion of sec. So what is k upon n? K means selection out of total number of n, which means proportion of success. It means p, right? So p equal to k upon n. So can I write this mu as np? Yes, I can write. So what is Q? Q is 1 minus P, right? Which means 1 minus K upon N, which means N and N minus K, right? So which is this term, right? So can I write this one as NPQ, just like in a binomial? Oh, I can just write N, P, Q, and N minus N upon N minus 1. So this is the difference between the variance of a hypergeometric and variance of a binomial, right? So now at this point, if K upon N is exactly the P, the proportion of success, then we can say it tends to a binomial distribution with mean X and NP, right? Parameters NP. So here, these are the parameters N, K, N. These are the parameters, and mu is N, K upon N. K is given, small n is given, big N is given. We will see in an example. And mu is parameters of a hypergeometric. Parameters are N, K, and N, right? And variance is sigma square. Now, if n tends to infinity, and K upon N is fixed, P is fixed, then see what happens. This is NP, we know that, because K upon N is fixed, and which is possibility. But in this case, if N is infinity, so this number will be really minimal. So it can change, it will convert into a binomial, and which is NPQ, right? So if N is infinity, it means N minus N upon N minus 1 is really minimum. It tends to zero, right? Not zero, but tends to zero. So it converges again towards the binomial, Poisson, hypergeometric, binomial distribution, right? So that's about the hypergeometric distribution. Do you understand this one? If you do understand this one, then I will take you back away from the whiteboard and towards the share screen, right? So continue. Okay. That's how we define Poisson distribution. I just didn't do it at that moment. So the hypergeometric distribution determines the probability of X event of interest when sampled data without replacement from a finite population. Right, so next time we will do the continuous random variable, and we see how we can get different kind of distributions, and we will solve some examples as well. Right, so next time we will start the continuous random variable. So this ends up your chapter 5 from the book, and you can have an overview of the things. So one more thing, like if you consider the Poisson distribution, we have talked about the Poisson distribution. That's also kind of a conditional probability, right? Because the other one we don't replace. So that's the information we have.